So good day everyone. In this video, we will discuss about the set complement and the set difference. So let's start with the set complement. So suppose we have a universal set U and a set A. The complement of a set A is A bar. So the complement is denoted by this bar equals X such that X is not in A. So it can be graphically shown in using this diagram. We have a universal set which contains the set A. So if this is A, the complement of A will be those elements or those parts that are not in A. Okay, so you can think of it like a negation. So if this is A, and then its negation will be those elements that are not within this set. So the complement of A will be equal to U minus A, where U is the universal set. So what if we take the complement of an empty set? The complement of an empty set will be the universal set, and the complement of the universal set will be the empty set. So essentially, picture it out. We have a universal set, and we want to take those. The universal set is the set that comprises everything, all of it. So if we take the complement of a universal set, we will be left with nothing. Okay. So, but if we have an empty set that has nothing, and if we take its complement, and it will give us the universal set. Okay. So what if we have two sets A and B, and we want to take the complement of B? So the complement of B will essentially be those elements that are not in B. Okay, and what if we want to take the complement of A? The complement of A will be those elements that are not in A. Okay, so suppose we have a set A with elements A, B, C, and D, and U is the set of English alphabet. So what will be the complement of A? The complement of A will be those letters that excludes A, B, C, and D. So that will be those letters E, F, until Z. Okay, so suppose we have an set A, and set A contains X such that X is an integer and X is odd. And assuming that the universal set is the set of all integers Z. So what would be the complement of A? The complement of A would be those elements X such that X is an integer and X is even. Okay, so again, there is no such thing as a number that is both odd and even. So if it is not odd, then it will be even. If it is not even, then it will be odd. There are some properties of the complement sets. We have the complement of A will be equivalent to A. So that is the complement law. So if you are familiar with, and I know you are already familiar with the double negation. So we are essentially like taking the negation of an existing negation. So it will revert back to its original set A. So taking the union of A with its complement, it will result to a universal set. And the intersection between A and its complement will be an empty set. So let us see. So we have here a universal set, and then we have a set A. And taking the union of A, so A is the one in the circle, in its complement is everything that is outside the circle, right? So taking the union, meaning we are combining elements that are both in A and the universal set. So this will give us, as you can see, the universal set. And we also take the intersection of A with its complement. So we can see that there is nothing that is common between this set A and its complement. So we can say that the intersection between the two will be an empty set. So now let us move on to the set difference. So the set difference is denoted by this symbol A minus B. So if we take the set difference between A and B, so we are essentially taking those elements that are in A but not in B. As you can see, here is the detail here. We are also taking the elements that are both in A and B because those elements are also in B. So we only want those elements that are unique to A. All right. So what about for B minus A? So we are essentially taking elements that are in B but not in A. Okay. So for sets A and B, the difference of A and B written in this form, A minus B, is the set of all elements that are in A but not in B. Okay, so formally, A minus B is a set of all x such that x is in A, and x is not in B. On the other hand, the B minus A is the set of all x such that x is in B and x is not in A. Right? So the difference between A and B, A minus B is equal to A intersection and the complement of the B, while B minus A is equal to the A complement intersection B. So let us picture this out. This is for A minus B. Why is it equivalent to A intersection B complement? So this is the set A, okay? So highlighted in gray, the set A. And the B complement. The B complement are those elements that are not in B. So now, what are the common elements between these two? So the common elements are this part, right? So this part, both highlighted by gray. So we can say that we can see that is very much the same with the plot of A minus B. Okay, so we can say that A minus B is equivalent to A intersection B complement. So likewise, B minus A will be equivalent to A complement intersection B. Okay. Now, suppose we have this example, 1, 2, 3 minus the set 2 and 4. So what are elements that are unique to this first set? So the elements that are unique to this first set are 1 and 3, since 2 is also found in the set 2. So now, z, or the set of integers minus the set of all x such that x is odd. Okay, so this will be equivalent to x such that x in z and x is even. All right. So the symmetric difference of the sets contains all the elements in either set but not both. So it is like the exclusive OR, if you remember. And so we know that the exclusive OR is denoted by the symbol XOR. So we also denote the symmetric difference between the two sets A and B as A XOR B. So formally defined, the A XOR B is a set of all x such that x is in A, but x is not in B, or x is in B, but x is not in A. So we know that these are essentially just definitions or formal definitions of A minus B and B minus A. So we have the A minus B union B minus A, right? So graphically shown, this is how it looks like. So we are taking all the elements that are either in A or in B, but not those elements that are both in A and B, right? We have this theorem AX or B such that it's equal to A minus B union B minus A. So how can we prove this one? So we are going to use the definitions of the set difference and the set union in order for us to prove this one. So by the definition of AX or B, we have AX or B is a set of X such that X is in A and X is not in B, or X is in B but not in A. So we know that this is a definition of A minus B. As you can see, X such that X is in A and X is not in B. So we can replace that with A minus B, right? And then on the other hand, X is in B and X is not in A is simply just the definition of B minus A. So we replace that with B minus A. Now, by the definition of union, so we have the union A of A and B is equal to X such that X is in A or X is in B. So this is essentially equivalent to the union of the set A and B. So we can then rewrite it as X such that X is in A minus B union B minus A. Now, we can rewrite this into this form, A minus B union B minus A.